This mini-lesson is the first of several designed to introduce problem-solving techniques for analyzing one-dimensional motion at constant acceleration. In many real-world situations, the acceleration of an object of interest is constant, either exactly or to a very good approximation, over the time interval of interest. Solving for the motion of the object in these situations is rather straightforward, as we shall see. Usually, we are given some information about the initial and final events of the motion and are interested in determining various other quantities associated with these two events that were not given in the problem. In general, the quantities associated with this type of problem include the time, position, and velocity of the object for both the initial and final events, plus the acceleration of the object, which is constant throughout. A couple things to note. First, we're free to choose the origin of coordinates and time as we see fit, as long as we stick with that choice throughout the problem. It's almost always convenient to choose the time of the initial event to be 0, and it's often convenient to choose the position of the initial event to be 0 as well. Second, please note that I've chosen S as the generic name for the position variable. If the motion is horizontal, we'll often choose to call the position variable x, and if the motion is vertical, we'll often choose to call it y. Don't let that confuse you. These 7 so-called kinematic variables, or 6 if we choose t0 to be 0, and 5 if we choose both t0 and s0 to be 0, are related to each other in constant acceleration motion problems by the 3 constant acceleration kinematic equations shown here. These were derived in a previous lesson, and they're the workhorses of constant acceleration problems. Let's do an example. A car is driving along a straight horizontal road at a steady speed of 45 miles per hour, which is about the same as 20 meters per second. Suddenly, a deer runs into the road and the driver slams on the brakes to avoid hitting it. It takes 2.5 seconds after the brakes were applied for the car to come to a stop. Part A asks, what was the car's acceleration during braking? And Part B asks, how far did the car travel while braking? Our first step is to parse the problem to determine what the initial and final events are. We are told the car's speed when the driver first hits the brakes, and we're told the time at which the car comes to a stop, provided, of course, that we set the 0 of time at the moment the brakes were first applied. We're also implicitly told the final speed of the car. It's 0, because we're told the car has stopped. So it's pretty clear that the initial event is the brakes being applied, and the final event is the car coming to a stop. We are asked to determine the acceleration, a, in Part A, and the total displacement, x final minus x initial, in Part B. The next step in this problem, and in most physics problems, is to sketch a picture of the situation described in the problem. You may be thinking that this problem is too simple to bother with the sketching a step, but I assure you the effort is well worth it. Indeed, you'll find over time that the sketching step of problem solving is of immeasurable value in organizing your thoughts. And don't worry, you don't need to be a good artist to draw a useful sketch. Notice that I've drawn the initial and final events in parallel to show their relationship, and I've annotated as much information as I can. Now that we have a good sketch, we're ready to develop a model that keeps the essential information and eliminates the extraneous information. In this problem, it doesn't really matter that the object in question is a car. The engine, wheels, doors, etc. aren't important for what we're trying to determine. Furthermore, the presence of the deer, while crucial to the actual scenario, is irrelevant to solving the problem. So let's eliminate the deer and model the car by a particle, or dot. In this simplified illustration, the dot on the left represents the initial event, and the dot on the right represents the final event. The object initially has a velocity to the right, which I represent by an arrow. At the end, the object has stopped, so there's no arrow. Below each dot, I list the kinematic variables for the initial and final events, respectively, and in between I list the acceleration, which, as I said, is constant throughout to a good approximation. Note that I've chosen the origin of coordinates and time to be the first event. I've also implicitly chosen the positive x direction to be to the right. How do you know this? Well, the object is moving to the right, and it's listed as having a positive velocity. The unknowns are indicated by a question mark. With our model in hand, we no longer need the written out problem. We're ready to solve. In part A, we're asked to determine the car's acceleration during braking, or in other words, find A. Since we know the initial and final times and the initial and final velocities, it makes sense to use the second constant acceleration equation because it relates these quantities to A. It's tempting to start plugging in numbers, and frankly, for a problem as simple as this, that would be fine. But you should get used to leaving everything in terms of symbols until the very end, and then plug in numbers. This is how professional physicists and engineers do it, and you'll come to see the value of doing it this way as problems become more complex. In this case, it's quite simple to solve for A in terms of the other variables. Now we're ready to plug in numbers and evaluate. The calculation finds a value for the acceleration of -8 meters per second squared. But does that answer make sense? After any calculation, it's a good idea to assess the answer you get for reasonableness. This step is often essential for spotting errors in your work and for making sense of the physics. First, does the sign of our answer make sense? The car started with a positive velocity and ended with 0 velocity, so the change in its velocity is negative. Since acceleration measures the rate of change of velocity, we would expect the acceleration to be negative as well, which indeed it is. Let's next check the units. Checking units is easy to do and is extremely useful for spotting mistakes. The quantity in the numerator of our calculation has units of meters per second. The quantity in the denominator has units of seconds. Dividing meters per second by seconds gives meters per second squared, as the answer shows. And indeed, meters per second squared is a unit of acceleration. So the units are consistent. Now let's move on to part B. Notice that I've updated the figure to include the newly calculated value of acceleration. Our goal in part B is to determine the distance the car traveled while braking. Since we have chosen to call the initial position 0, the distance traveled is just x final, the last remaining unknown kinematic variable. Conveniently, the first constant acceleration equation gives x final in terms of the other kinematic variables. So all we have to do is plug in numbers and evaluate. Before evaluating, let's look at the units of each term. Remember, you can only add numbers together if they have the same units. The first term is 0, so we ignore it. The second term multiplies meters per second by seconds, which gives meters. The third term multiplies a pure number, 1/2, by a number with units of meters per second squared, and then by a number with units of seconds squared. Thus, this term has units meters per second squared times seconds squared, which is meters. Since the two non-zero terms have the same units, we can add them. Evaluating gives a total displacement of 25 meters. Does this make sense? Well, the average velocity, given by averaging the initial and final velocities, is 10 meters per second. A car traveling at an average velocity of 10 meters per second for 2.5 seconds would indeed go a total of 25 meters. So our answer checks out. This was a pretty straightforward problem in constant acceleration motion, but hopefully it got across some of the important strategies in solving physics problems. In upcoming examples, we'll look at more complicated situations involving constant acceleration in one dimension.